Okay. Hello, hello. One sec. Hello. Okay. Oh,
Good
good
morning.
morning. Oh, nice. Okay. Good morning, Gabriel. Okay, let's do this.
Morning.
Oh, that was even, the triple. I mean, all right. Gabriella, good morning. And Jocelyn, good morning. Sydney, good morning. Effie and Cartman, good morning. Melanie, good morning. Norma, good morning. Hold on. We're going to do this. Mohammed and me, good morning. Angel, good morning. Okay, chat. Quit. Oh, more people. We're gonna do this. Um, why? Okay, Angelina. Good morning. Effie for the double and Cartman for the. Screw you guys. I'm going up. Melanie. Good morning. Gabby. Good morning. Angel for the double. Good morning. Teresa. Good morning. Sinead with the all caps. Good morning. Zebo, good morning. Sydney, good morning. Nadine, good morning. Jocelyn for the double, good morning. Triple, good morning. Jean, good morning. Genesis, good morning. Chanel, this is a full house. Good morning, Chanel. Good morning, Christopher. Good morning, Norma. Mohammed, good morning for the double, triple. Good morning, Joshua. Good morning, George. Good morning, Lunar. Okay, on the full moon, I believe, as a matter of fact. I won't talk about it for 20 minutes, or will I? Okay. Um, Let me just switch the view on this. Okay, we're gonna get rolling. So, a couple of things, as I mentioned, I don't have your exams yet. It's gonna be a little while. Please bear with me. I don't know. They'll come when they come, and they will come, but it's gonna take a bit. Um, but I will say very quickly, I think I put in so we're going to move on with the material in a moment. Um, you guys are a great class. I mean, I have not, I do, I'm not reporting on exam particulars, um, but I want to I really want to emphasize something that I put Reese in the stream of Google Class or somewhere I put in the Google Classroom. You may or may not have seen it, which is that, um, you know, I, I have a number of times now, I always have these Zoom videos scrolling on my screen, honestly, like in the background, when I'm walking through the house, honestly, partly so that I can see, how long it takes me to get to a point and how long it takes me to get to the next slide, like to improve as a teacher and it's mortifying to see how long it takes me to get to a point. The only thing that's more mortifying than that, you should know, is is the fact that it's an improvement. It used to be even way worse. Actually, you may know that if you see old videos. Anyway, but just know that I know, and I'm anyway. So, but as a result of that, I scroll through all the videos from all the classes all the time, just in the background, and I don't listen to myself any more than you listen to me. But the Zoom that you guys made, um, held and recorded, for the purpose of this exam, so that has scrolled in the background a number of times. I want you to know I am intentionally not listening to it I'm not looking at what anybody or hearing what anybody particular said about any problem because I don't want to be biased. I don't want you to think that I think that you did know something or didn't know something, and I wanted you to be free to conduct yourself without worrying about my judgment. So I'm sticking with that. So I don't know what you said about any of the particular problems, but I certainly do see like that people participated in. I see how well managed it was, and how much initiative so many of you took to participate with each other and scroll through problems and stuff, and it warms my heart. It's super impressive, honestly. And I also know that even if you're not appearing in that Zoom, that doesn't mean you didn't study or do other things with other. I also know there were other independent things that were going on. I think it's wonderful, and I think it's hard. So I'm just saying that, like, um, anyway, so you should know that I know, and I care. Okay. So now let's get back to material. Switching the view on the screen. Hold on a second. Pardon me. Yes. Okay. Um, where we were, and I'm going to get back to there is a homework that's due The most recent homework, I know there's a lot of it we sort of didn't go over. I'm aware of that, but that was for good or for bad, that was material that was then just covered in this exam that you just took. And we're moving on now. It's all connected, but we're moving on now to Newton's laws, and there is a homework for Newton's laws due, in 2 days. As always, I, I ask you to make your best attempt of a first draft, get it in on time, and then we'll be continuing to talk about the underlying issues, and you'll have more time to revise and improve and get more points. And I think many of you have noticed that that's been happening. Like in one way or another, as long as you do revisions and sometimes even just respond to formatting requests that I've made or whatever, you eventually get all the points. So, in other words, I'm saying I'm getting into the Newton's laws stuff now. Of course, it gets very mathematical. Last class, we had a very, you could say, conceptual discussion about the meaning of Newton's first law of motion. And the ultimate punchline of that discussion, and I do think this is new to some of you, even if even if you did physics in high school or whatever, the punchline is that Newton's first law of motion, the base case, what objects do when they are by themselves, not interacting with other objects, what they do, I'm telling you, is a way to understand it is they obey Galileo's principle of relativity. My argument, the ultimate punchline from the last class, is that what we know as Newton's first law of motion really can be understood as the sixth form of Galileo's principle of relativity. And you are responsible for knowing the first five. They were covered in the first exam. Um, I um, I believe it really doing physics, solving Newton's law, solving problems involving Newton's laws is best managed or most helped if you understand that the reason object that if you understand that objects do not require help to move. They do not require outside influence to keep moving. It feels that way. It seems that way. It seems like to keep something going takes energy or force or fuel, but it's not actually the case. To keep an isolated object moving, to keep an isolated object moving, doesn't require anything. To speed up an object or turn an object or slow down an object requires an influence from the outside, from another object. And the best way to really understand why that's true, I'm just summarizing again and I'll move on. The best way to understand why that's true is that what we're really saying is anything that you do understand, anything that you do expect of objects that are just sitting still applies equally well to objects that are moving because sitting still or moving is in the eye of the beholder. That's what we're really saying. Good morning. Awesome. Thank you. That's what we're really saying. It's a deep point. I am not saying it's an obvious point. I'm saying it's a true point. But I'm saying if you really understand Galileo to mean zero velocity, non-zero velocity, this is a matter of perspective. No object has a velocity. Objects only have velocity in relation, in comparison to other objects, or from the perspective of other objects. Once you really understand that there is no special zero velocity, there's no center of the universe. There's no object that is actually sitting still objectively in space, right? That's what Galileo is really trying to tell us. It felt like the Earth was that, but the Earth is not that. It feels like the Earth is stable, but the Earth is actually moving at 65,000 miles an hour past the sun, which itself is moving at 650,000 miles an hour past the center of the galaxy, et cetera, et cetera. So the point is, zero is not a thing, is what we're really saying with Galileo's principle. Therefore, whether an object is at zero or not at zero, it still obeys the same tendency, the same expectation, the same natural state, which is to not change its velocity until influenced by another object. Okay, that so I'm saying that Newton's first law of motion is really just the sixth form, is just another way of saying Galileo's principle of relativity. That's what the first law is. Now that's the summary of and think about again, it's simple, but it's not easy. It's conceptual, it's not mathematical, but that doesn't mean but let it sink in, whatever. That's the result from last Wednesday's class, or whatever time we had. Okay, then so that's the first law is GPR form number six. Now I wrote down the second law and the third law, and you've heard them in high school or other in the world, you've heard them. I wrote down the second law and the third law. The second law is the super mathematical one that really then allows us to do all these mathematical problem solving from here on in physics. That's like the meat of physics is the second law. So that's what your homework and everything is all about. I want to get to that. But since I wrote it down already, you know what it is. And I actually, and sorry, in one form, it's written right here in the middle of the board. In a way, right? Okay, just to be clear, this, just to be clear. Well, okay, no, I'll go on and say to repeat what I said last time, like Newton's second law of motion in its like proper form is the sum of all of the force vectors acting on a mass yields the acceleration vector of that mass. Like that, right? Like the second law is what I just wrote here. Now we're going to expand this like for the rest of our lives in a few minutes. We're going to expand this. But again, just to sort of summarize something I said last time, like, I know you've all heard, and I mean, I know there's t-shirts and jokes and necktie where people say force equals mass times acceleration. The two things I'm trying to emphasize here, if we're doing physics properly, is that first of all, it's not force that equals mass times acceleration. It's net force that equals mass times acceleration. It's the sum of all forces acting on an object that equal mass times acceleration. That's what the big sigma there is meant to say. You could also say, if you prefer, you could say F net equals M. Like if you look these things up on the web or ask ChatGPT, right, like it would say it one way or the other. The key is that acceleration of an object is the result of all of the forces being added up, acting on that object. But then the second point, the arrows in the equation are trying to remind us that each one of these forces is a vector, right? That the sum of all force vectors yields the acceleration vector of a mass, right? And the thing about, oh, and sorry, there's something in the, oh no, that's a hello. The thing about vectors that you've been studying is that, first of all, vectors mean not just magnitude, but direction, right? And they mean direction forward or backward on any and all of three axes of space, acting independently yet simultaneously, right? So it's a vector equation. So when we say adding up all the forces, we mean taking into account minus signs, and we mean adding up all the forces on a particular axis yields the acceleration on that axis. That's why I think a more convenient way to break down Newton's second law is this way right here on the board, the second, to say what it's really saying is along the x-axis, the sum of all the forces, taking into account minus signs, yields the acceleration of a mass on that axis. And independently yet simultaneously, the same thing is true on the y-axis and the same thing is true on the z-axis, right? Okay, that's Newton's second law. Now, again, I'm saying it quickly, not because it's a small thing, it's a huge thing, but because that's really where I want to get to. Like I'm going to expand further and we're going to solve problems with, and that's what your homework is about and so forth in a few minutes. But before I get to all of that, let me pick up where I was last time and say a few things about Newton's third law, which is less mathematical, more conceptual, but really important. Well, Newton's third law, I wrote it very quick. I wrote last time, if I push you, you push me back with with the exact same force magnitude. A slightly more rigorous way of saying that is Um, so what it's my hand, my God, I'm sorry. What it says is if this is Newton's third law now. If object A exerts a force on object B, then object B exerts a force on object A of identical magnitude in the opposite direction. Okay? Um, one sec. Okay. Um, okay. First of all, something in the chat. Sorry, hold on a second. Okay. Oh, what a perfect question in the chat. Okay. And by the way, sidebar, there's a possibility that we may get sort of interrupted like right in the last 10 minutes of this class, like right toward the last few minutes of this class. And it's possible then that the interruption will be such that if it's that close to the ending, we'll just shut down sort of abruptly. I won't try to script. Okay. Possible that we're going to end a few minutes early, possibly. Just so you know. Um, um, but there's a great question in the chat. Perfect. Okay, thank you. I love it. Thank you. There's got to be a portal for that. Um, there's a great question in the private chat. I'm perfect question. I was just about to get to the. Okay. Okay. So let me read my handwriting, and then I'm going to read this question out loud from the private chat. So my handwriting says, a force I'm saying this third law, the reason I'm sort of going out of order, the reason I want to like talk about the third law before I really spend the rest of our time on the second is that arguably it's the third law that really tells you what a force is. The first law tells you what's happening to an object when there is no force acting on it. That's why I keep calling the first law like the base case. The first law is what happens to an object when it's by itself. The second law sort of tells you what happens to objects when they are influenced by other objects, i.e., by forces. But the third law sort of pauses and says, I mean, here's what we mean by a force. Okay. And 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 yes, someone has written in the chat, is this force the whole thing that you've heard of for every action there's an equal and opposite reaction. I was totally just going to, and so yes, it is. The third law is the whole action reaction thing that apparently at least one of you has heard of, and I think many of you have heard of. And yes, it is. And is it okay to think of it that way? Well, sort of. I mean, that's a great connection to make, but actually, yes, I am here to tell you that there's something limiting about like that I want to expand and clarify what's good and bad about calling it the action reaction law. Okay, so this third law, yes, is that action reaction law. But here's what it's really saying. What it's really saying is that, and what the handwriting in white says is a force. What a force is a symmetric interaction between two material objects, between two actual thingy things, between two masses. Okay? So a force is like not a thing. A force is not a mass, and a force is not something that a mass has. A force is a description of one mass interacting with another mass. Okay, one particle, one physical object, concrete, tangible, like a coffee cup, a baseball, a rocket ship, a planet Earth, an electron, like something that's real. When it interacts with something else that's real, that interaction between the two objects is what we call a force. What the third law is trying to say, very specifically, is that a force, first of all, is that for there to be a force, there must be one object interacting with another object. It definitely requires a pair of object, just like, notice, this is not a coincidence. Notice that velocity, like, is a relation between two objects. It's not a property of one. Similarly, a force is an interaction between two objects. It's not a property of one. Furthermore, what the third law is saying is that it is a symmetric interaction. It's saying that whatever one object does to a second is done by the second simultaneously right back to the first in magnitude. I mean, down to the numbers. Um, Now, this is that whole idea of action reaction that you've heard about. But the thing that I want to emphasize here before I go any further is when people say for every action there's an equal and opposite reaction, what that often makes it that's deceptive. That doesn't capture all the nuances of this idea. In fact, it can give a very big misimpression. I'll say quickly. When people say for every action there's an equal and opposite reaction, um, um, it can sound like okay, I'm gonna be. Wait, should I be really gross here for a second? Hold, let me just think if I can. I have an example in my mind that's like a little bit off color. I'm thinking quickly if I can give an example that's not off color. Okay, look, I'm just gonna say this. Oh, okay, I'm gonna rip off the Band-Aid. Okay. So like when I was in 10th grade, I was in the chemistry class in 10th grade when I was in high school, okay, like 1986. Okay. And there was a person in the class that I didn't like it. And one time, like while we're all like doing stuff in the class, that person sneezed really loud and then she flatulated at the same time. I mean, she farted, okay? And haha, like we all, okay, thank you. Okay, thank you for the, and I, like, we all took pleasure in that. Like, it was whatever. It was, I'm sure, embarrassing. But and the fact that I still remember it is sad. And I've got meta stories about this memory that are even sadder. But hey, here's the point. So she sneezed and she farted, right? And okay, I'm glad you like that. Okay. Now I've heard people say, I've even heard in Kurt Vonnegut books, people like if you've ever read people will say things like, ah, that's an example of Newton's third law. You action, reaction. Something goes to the north and then something else goes to the south. That is not an example of Newton's third law. And I mean it. Like what Newton's action reaction can make it sound to people. It can make it sound like if I push to the north, I necessarily have to put or if I'm pushed to the north, then I necessarily have to be pushed to the south or something like that. It sounds like if there's an action on an object, there has to be a reaction to that object. When people say for every action, there's an equal and opposite reaction, it can sound like they're saying, and they often believe that they're saying that whatever happens to an object must also happen in the opposite direction to that object. That is not true. That is deeply not true. If that were true, nothing would ever accelerate, if you really think about it. And I'm not trying to confuse you, but I am trying to correct an important misconception. The reason we write the law the way we do in a proper physics class is what we're saying is if I push you to the north, then necessarily you must push me to the south. That is do you see what I'm saying? What we're saying is that a force is a tug of war between two objects. And whatever one object does to the other does to the one. Neither one of them gets two forces. In other words, and I'm going to move on in a minute, you'll see this in practice and stuff like that. But the really important distinction I'm trying to make here is that the action and the reaction that you've ever heard about, oh yeah, it is a law. It's literally a law. There is no action without an opposite reaction. That is true. But you have to understand that they're on two different objects necessarily. They're not on the same object. If they were on the same object, that object would never accelerate. There would be no motion in the universe, right? So what we're saying is that a force is a symmetric interaction between two objects. What we're saying is if you push the wall, if you push against the wall, you go flying backwards, right? You push the wall, and that's how rockets work and things like that. Okay? And the surprise, and so we're saying, so what we're saying is, if you really think about it, we're saying if you really have been following sort of the thematic thread of this course, right? There's a thematic thread and then there's the math. And my argument constantly to all of you, a lot of people are afraid of the math in physics. I'm here to tell you the math is not the hard part of it, or at least the computation is not the hard part of physics. The hard part of physics is setting up the math. And I'm here to tell you that the way to set up the math is to follow the conceptual thread of physics that makes physics physics, the conceptual thread throughout, and I'm saying into the 21st century. What century are we in right now? Yeah, through the 21st century, the thread, honestly, is expansions and expansions and expansions on this idea that you could be standing on a rock that's going 65,000 miles an hour past the sun and you don't feel it. The more you peel away the layers of that onion, the more you know how to set up the computations of physics. So here is now the seventh form of Galileo's principle. We originally said, back in the third form or something, that velocity is a relation between two objects, not a property of one. Now we're saying similarly, force is an interaction between two objects. It's not a property of one. Force is not something that anything ever has. There's no such thing as the force of a baseball or the force of a baseball bat. There is the force that the baseball bat exerts on the baseball. And whatever that is, in whatever units of measurements, is exactly the same in magnitude as what the baseball does back to the bat. The same magnitude. I'm glad okay. That's okay. And we're saying, if you really think about it, it would have, and that's the surprise. The interesting information here that we're going to see play out in the math is that the magnitudes are the same. I'm saying when a baseball bat hits a baseball, the baseball hits the bat back at the same time with the same amount of strength. It may not seem that way because the baseball goes flying and the bat does not, right? But what that gets us into is the second law, which I'm about to get into. What that's saying is, well, yeah, the baseball has much less mass and the baseball bat has much more mass. So if you were to exert the same force on both of those objects, like what the second law is saying is that acceleration is inversely proportional to mass given a constant force. Do you see right? So you push the wall really hard and the wall pushes you back exactly the same hardness, but the wall's really heavy and you're really light. So you accelerate a lot in response to that and the wall accelerates very little. Hang on one second, something just came. I'm just going to check one thing. Okay, okay, okay. 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 Does that, and I'm saying that is just another extent, like once you really get this idea that that there are measurements in physics that are really, um, relations of between pairs, not properties of singletons, then you really get something, right? So this is the seventh form of that idea. And if you think I'm being repetitive, if you feel like it's the same thing over and over, yes, welcome to fit. Yeah, it is. It's just expanding. Okay, you get that. So now I want to wait. There was one other thing I was going to say. I want to now get to the second law and start applying this. But there was yeah, one's last stupid. As long as I'm making like dumb off-color analogies. Um, but again, if you're going to focus on anything as we move on to the second law, focus on that the impact of this is that the magnitudes are the same, even when they don't look the same. Like, in other words, the cause, like interaction is a cause, acceleration is an effect. And the second law is what maps out for us the relation between that cause and that effect. Um, but when things pull or push on each other, they pull or push on each other in the exact same way in both directions. And then the result of that is accelerations that can be different for both of the objects. Um, So the bottom line is this means that on any given object, the number of forces acting on one object could be an odd or even number. But but the number of forces of interactions in the universe is an even number, if you follow what I'm saying. Um, wait, I want to move to the second law, but there was stupid analogy, just if it helps. Like, I married my wife on October 20th, 2012. Okay. Well, guess what? My wife married me on October 20th, 2012. Duh, right? Like it's not a like yeah, of course, because marriage is that kind of a thing. If I married her at that time, then she married me at that time. It's that kind of a thing, right? It's just like a definition of the term. That's what we're saying. Forces are like that. Forces are just a symmetric relation like that. You can't do a force to something without it doing it back to you. It's a tug of war. Oh, and and I'll say lastly. What so a force from now on is a symmetric interaction between two objects. The English word, I mean the sort of more informal word to picture from now on. Oh, okay, wait, let me do this on the next page. Sorry. And then we're just repeating the same, is a symmetric interaction between two objects. We already said that. Um, between two masses, let's say for being, or you could say two particles. Um, Symmetric interaction between two, colloquially, every force, if you want to know whether there's a force happening in a situation, a force is a push or a pull, like literally, right? It's that. And what's the difference between a push and a pull? A push is away and a pull is toward. Okay. So you can't push without being pushed, is what we're saying, and you can't pull without being pulled. And finally, I'll say, as a signal, as an informal signal, as to whether a push or a pull is occurring in a certain situation, the signal is that unless we're talking about gravity, we are definitely talking about physical contact. Like you cannot push or pull an object with you cannot push or pull an object without touching it unless you are planet Earth. At least in the context of this course right now. I mean, there's other exceptions too, like magnets and stuff, and we get to that in Physics 204. But in the context of classical mechanics, the only way to exert a force on another object is to touch it unless you are planet Earth. Okay? And that's important. So how you can know whether like a force is happening or not. So we're saying like gravity from Earth, and other than that, physical contact. And please note, as I now proceed to Newton's second law, please note that even in the case of gravity, which is so mysterious, I mean, on the one hand, we're so familiar with it, we're all used to it, we all know it's there. On the other hand, it's sort of like, what is it? Like, I don't know. We'll get to that. But even the mysteriousness of gravity, notice that's still an interaction between two material objects. Look, when you talk about gravity pulling on you or on a baseball or whatever, you're talking about planet Earth, which is a material object, pulling on what? Oh, pulling on the baseball. So even there, so in other words, what I'm trying to emphasize before I move on is even when we talk about something that seems as disembodied or as abstract as gravity, we're still talking about two objects that are interacting, pulling on each other. Okay? That's what Newton's third law is trying to say. Now, we still have strangely, 30 minutes. So now let's expand on Newton's second law, like for the rest of our.
Professor, can you kind of go back and like re-explain the whole thing with gravity again? I didn't really get it.
Wait, sorry. I'm totally glad that you just, and thank you. And I love how that picture just popped up. Okay. Um, yes, but wait, could you repeat? I know you're asking me to you're asking me to repeat or re-expand just say the thing about
Uh,
gravity again? Is that what you?
Yeah, just like repeat kind of what you said.
Okay. Well, what I said was even gravity. See, gravity is funny because gravity is the one and only one force that will ever come up in this class. Gravity is the only force that will ever come up in this class that doesn't seem to involve two objects touching each other. On the one hand, that is what's strange and mysterious and maybe confusing about gravity is that the two objects involved in any gravity situation don't have to touch each other in order for them to pull each other. So on the one hand, that's what's exceptional about gravity. And I want to note that. Like that is an exception. I'm saying any other time you're ever looking to see is there a force happening here, you would look for physical contact between two objects. In the case of gravity, no. You don't, there is no physical contact. The pull just seems to happen through empty space. Okay, so that's the confusing thing. On the other hand, I want to emphasize that even in that case, even in the case of Earth exerting gravity on an object, it still is two material objects interacting with each other. In other, right, it's still Earth pulling on a baseball or a bomb or an airplane or whatever, or you. Like when we talk about your weight, we are talking about planet Earth pulling down on you. So why am I like making a point of that? I'm making a point of that to say there's no such force in the world at all that just exists on its own. You never are just, it's not like Star Wars. You're never just pulled. You're always pulled by something. So even in the case of gravity, you are pulled by Earth. Or if we went to the moon, we'd be pulled by the moon. We're not just being pulled. Does that tell me honestly if that? So I'm just trying to emphasize that Newton's third law is saying a force is an interaction between two actual things, always, even including gravity. Does that make sense?
Yeah, it makes sense. That makes sense. All right, thank you.
Awesome. All right. No, thank you for the. Okay. Awesome. Okay. So now I'm going to go back to Newton's second law. Like we're going to expand on this, and it'll start getting us into the homework. I hope. I think. Um, But again, summary of where we are now, class, folks, everybody, Mohammed, everybody. Um, Everything in this class conceptually is some version of, and will continue to be some version of Galileo's principle of relativity. I'm saying you now have seven forms of it. And the last two forms, like six and seven, are known as Newton's first law and Newton's third law. Newton's second law is its own thing that I'm now going to get into, and it's very powerful. Like again, Newton's first law says what happens when there is no force acting on an object. Newton's third law says, oh, nice, nice, yes. Newton's third law says what a force really is. And now Newton's second law will tell us, okay, what is the mathemat? Oh my God, I just learned what, okay, sorry, I'm not going to get distracted even though I totally am. I just learned this weekend about that 6-7 meme thing from my, okay, I'm not even allowed to talk about it. I'm so behind, but my son explained it sort of to me this weekend. All right, I'm not going there. But yeah, I sort of get it. Sort of. I'm so old, Lordy. Okay. Yeah. Okay. Emotional damage. Okay. That guy's hilarious. Okay. Newton's second, I want to be him. Okay. Newton's second law of motion, which is again is this. Okay. Okay, hold on. And for this, I've already made a bunch of comments on it, so I think I want to start showing you how to apply it. And in order to do that, I think it might even be possible. Let's see if I can help you. I'm going to open the homework. Hold on one second. I might be able to help with some of this homework. if it's what I think it is. Okay. Yeah, I'm gonna start walking you through the homework that's due this Wednesday. That'll be the most concrete way to start really expanding this law. Um, okay. I'm just thinking about whether I'm screen. All right, yeah, I'm looking at the homework. I may screen share it in a second, but but first it asks in the homework, like, what's the mathematical definition of a Newton? Like, what's the units and everything of force? All right, I'm basically going to do it for you right now. Like, like units, and I hope it's clear. I don't know if I've done this before, but whenever I put square brackets around something, that means I'm talking about the units of that thing, right? So, so on the right side of Newton's second law, MA, the units are kilograms times meters per second squared, right? Mass is measured in kilograms, um, and acceleration is measured in meters per second squared. So force must be measured in a unit that constitutes that product. Well, that unit is called a Newton, not coincidentally. So literally 1 Newton, by definition, is 1 kilogram times 1 meter per second squared. What does that mean? It means that's how hard you would have to push a kilogram of mass in order to accelerate it at a rate of 1 meter per second squared. So if you figure that like a big apple is like literally a piece of fruit is like around a kilogram in mass, what we're saying is if you took that apple, held it in your hand, and then moved your hand rapidly enough from rest to get your hand up to 1 meter per second of velocity in a second. And 1 meter per second, okay, is about is about 2.25 miles per hour. So you're going to move your hand rapidly enough so that within 1 second, it's now moving about 2.5 miles per hour. What To do that to an apple is to exert a Newton of force on an apple, if that puts it in any kind of perspective at all. That's what a Newton of force is. Um, uh, Notice then, so from now on, if I was saying Newton, that's what I mean, a kilogram times 1 meter per second squared. Notice then mass, what mass really is. Mass, as you've heard in high school and so forth, mass is an intrinsic property of one object. What mass really is the ratio of net force to acceleration. Like you're often a word that people use for mass is inertia for this kind of mass, meaning what mass is resistance to changes in motion, right? Your mass is how much you don't want your velocity changed. Like the more massive you are, the harder someone has to push on you to get you to accelerate, to speed up or slow down or change direction. And notice how I keep saying velocity is not a property of one object, it's a relation between two, or force is not a property of one object, it's an interaction between two. Well, some things are properties of objects. Mass is one of them. Mass is a property of an object. An object has mass, a certain amount. And even if you move that object to the moon, it still has that same amount of mass, right? If it takes 1 Newton of force to get it up to 1 kilogram per, I mean, to 1 meter per second squared of velocity down here on Earth, then the same thing, it would take the same amount of force on the moon. Okay, so it's resistance to changes in motion. That's what mass is. Arguably, it's I'm arguing that acceleration is defined by calculus, force is defined by the third law. So the ratio of the two is really the definition of mass as outlined by the second law, if you want to think of it that way. Okay, I'm going to just go on with um sorry, let me say please also notice well well I don't know how to I'll just say quickly. In Newton's second law, what we're saying is the forces that act on an object produce the acceleration of that object, not anything else. We're not saying that the heavier you are, the more you have a force, or the heavier you are, the more you can exert a force, nothing like that. We're saying the heavier you are, the more you resist forces acting on you, for whatever that's worth. Okay, so I'm going on with the homework. Okay, this is homework 7, sorry. Hold on one second. Yeah. Okay. So then in question 2, the warm-ups, it says force warm-ups. Um, okay, I guess I'll do a quick screenshot so that you can see what I'm talking about here. I'm looking. Oh, okay. Thank you for the oh my God, all the chat responses. Okay, I see the chat and I see the direct chat. I think that person's already okay. But let me just do a quick screen share so you see what I'm talking about. Okay, so I'm talking about this homework, right? I just sort of answered question 1. Now I'm on question 2 right here. Um, um, okay, punter punts a football. The football weighs 1.5 kilograms. The football is now flying through the air. It's no longer in contact with anything. Okay, and we're assuming, somebody asked last time, we're not talking about air resistance or anything like that because the football, yeah. Um, uh, so first of all, so the football is in free fall. So we want to know the football's acceleration in magnitude and direction. I'm going to switch the screens again in a second, but I'm going to tell you, remember our definition from even before we knew about any of this. Free fall means there's no forces acting on, there's no influences acting on an object whatsoever. No objects are touching the object whatsoever other than the pull of planet Earth known as gravity. That's what free fall means, that the only thing acting on an object is gravity, right? So if it's saying here that the football's in free fall, that means its acceleration is 9.8 meters per second squared or 10 meters per second squared, pointing straight down. Like that's it. That even though the football might, and even though the football might be moving through the air at this moment in some horizontal way, this is like lab 4 or whatever else. At any this moment in time that we're talking about, the only acceleration would be straight down toward the surface of the earth. So I'm gonna switch screens now. That's important. Like there's no like you might have kicked the football like 5 minutes ago. So when you were kicking the ball, maybe you were exerting a force on it. You were touching it. But now you're not touching it anymore. So at this moment, nothing is happening to the ball except for gravity. So I'm switching screen. I'm going back to the screens. Oh, I'm sorry. So that's that's question one. I mean A sub one. So then two on the homework then says, okay, so if that's the acceleration, then according to Newton's second law, what's the force that gravity must be exerting on the football? Okay, this is like a little, this is very important. Um, Newton's second law. So this is our first example of actually doing it. Newton's second law says this, right? Which really means that the sum of all of the forces along each axis independently produces the acceleration along that axis. Okay, so there's only one axis where anything is happening here. It's the vertical axis, the y-axis, right? So I'm going to say the sum of all the forces on the y-axis equals the acceleration on the y-axis. Okay. Um, and um, And the only, so now what we're supposed to do is on the left side of this equation, we're supposed to write down every single one of the forces that is acting. There's only one force acting. It's the force from planet Earth, which we often call gravity, or from here on in, we're also going to call the weight of the object. I'm going to say the only force acting on the object now is the weight. Again, please note the foot of the football player that kicked the ball, like that might have happened 5 minutes ago, but that was a force then at that moment. It's if nothing else is touching the ball anymore, then there's no other force on it. The only thing is the force of gravity from planet Earth, which from now on we call weight. In fact, so on the next page. Sorry. So from now on, I'm saying weight is a word for force, the specific force of planet Earth pulling down on an object. So, right. So in other words, well, you get it. So weight is not mass. And you've heard this before too, right? Mass is an intrinsic property of an object wherever the object is in the universe. It's But weight is a specific interaction with that object from planet Earth. Or if you were on the moon, it'd be the specific gravitational interaction from the moon. But weight is a pull. And even if we make it sound like it's just something you have, like if we would say your weight, we're tacitly always referring to the fact that Earth is interacting with you. Okay? So in Newton's second law here, I'm saying, so here, back to this example, I'm saying weight of this football equals the mass of this football times the acceleration of this football down to Earth. Okay, but we just said that the football's in free fall. So the football's acceleration is that number g, that number 9.8, which we often call lowercase g, right? So we're saying the weight of this football is its mass times the acceleration due to gravity. In other words, weight is a force measured in units of newtons, and and newtons are measured in are 1 newton is 1 kilogram times 1 meter per second squared, right? So I am saying that the weight of this football, sorry, so the mass of this football in this case was like 1.5 kilograms, and gravity is approximately 10, is 9.8 meters per second squared, which is we're going to call 10 to make this point clear. I'm saying in this case, the answer to the homework question is the force that gravity must be exerting on the football is approximately 15 newtons. But my real takeaway here is twofold. One, I'm saying we would call that from now on the football's weight. Notice if the mass of the football is like 1.5 kilograms, the weight is like 15 newtons. They're measured in different units and they differ by 9.8 or approximately 10 meters per second squared, right? And I'm saying that, so number one, I'm saying that. Number two, I'm saying that is in general now a truism going forward. From now on, from now on, weight of an object equals the mg of the object, not the m, not the g, but the mg of an object. Your weight is your mass times 9.8 or 10 meters per second squared. Mass is an intrinsic property, weight is a force. Mass is measured in kilograms, weight is measured in newtons. Okay, and weight is how hard you'd be pulled if you were in free fall, i.e., it's how hard you'd be pulled if the only pull on you were planet Earth. So, what weight is the pull of planet Earth. I'm going to say this one last way and then move on. I'm saying, even if other things were happening to this football, even if there were other pulls or pushes on it so that it wasn't in free fall anymore, we just analyzed free fall so we could isolate the effect of gravity. So from now on, even if other things are happening to an object, the object's weight is still its mass times 9.8 meters per second squared. Okay, and that's a force. And it's the force from the center of planet Earth from now on, always. And the reason we just like did all of that, I know we have 15 minutes left. The reason we did all that is because, kind of like I was saying to Muhammad and everybody else a few minutes ago, like gravity is like always with us. It's in every problem, it's in every situation in physics because we're always like on Earth. So gravity's always there and it's always relevant to every calculation, but it's a little bit exceptional because you never see it act. You don't see the two objects touching. So we want to just right away make this recognition that every object always has weight. It's always being pulled down with a force of its own m times g. And that's going to be and now that we know that, we can go on and look at every single other force, which will involve physical contact and touching. Okay, so that's that. That's that homework problem. Um, uh, Now I'm going to let you do 2B, like the next pro you can do the it's like a plugin. It's not meant to be a trick. It's just a practice plugin. You can do that when you do the homework. But now let me move on to diagrams. Well, thank you very much. So I'm going to go to 3, which is diagrams. Very important. Um, okay, so in problem 3, we I'll just summarize. I'm not going to screen share again, but it says we have okay. So first it asks, so we have an apple sitting on a table. The apple has a mass. Even that, it's weird. It says the apple weighs 0.5 kilograms. Like that's English. That's the way people talk. That's a little confusing. What we're saying is that the apple has a mass of 0.5 kilograms. And I'll tell you right now, even before the thing asks, that means its weight is essentially 5 newtons, if you're following this discussion. Okay. But anyway, it tells you that, and it says the apple's not moving, and it says it's on a table. So it asks you to draw a picture. Just like first, just an informal, like, step one DFP, an informal picture. So here's my informal picture. Here's a table. Here's an apple, and it's 5 kilograms. Or I'll even, it has a mass. And the mass is 5 kilograms. Okay, so that's my informal picture. But then it starts asking for more formal, ultimately, it asks for two things that I wanted to find for you now in the 11 minutes that we have left. It asks for two types of pictures that, of course, you can look up on the web and stuff like that. But the two types of force diagrams that it asks for that we're going to use a lot. There are two distinct types of force diagrams, and they perform two different functions. And we do them in order. Like we always, whenever we're trying to make predictions and solve physics problems involving forces, it's ultimately all about Newton's second law. But what Newton's second law is all about is knowing what to plug in on the left side of Newton's second law. See, here's the program. Here's the larger program. We're trying to we're the whole first unit of this whole class or first set of units was ultimately all about the accelerations of objects. It was all about like if you know the acceleration of an object, can you predict its future velocity or its position? Wait, I'm going to pause for a second. This is the interruption. We're not going to end class. I'm just going to pause. Oh, sorry. And I see the chat. Hold on. I'm going to pause for a second. Okay. Wait. So I'm going back to Newton's second law. I know we have 8 minutes, but wait, there's things in the chat. Would it be wrong if it were negative? Would it be? Oh, really good question. I think I know what the direct chat. Would it be wrong if it were negative? I mean, it's a great question. Strictly speaking, you're right. No, I get it. Yeah, yeah, yeah. I mean, good question. Strictly speaking, from here on in, the negative sign, the reason we're going to do these diagrams now, and obviously we're going to, end in 8 minutes, but I'm pausing because it's okay. What I'm trying to say is from now on, we're definitely paying attention to negative signs and positive signs for sure. Negative is one way, positive is the other way on any given axis for sure. But from now on, once we get rolling with all this, you'll put the negative signs and positive signs on forces. Like one force will be going in a positive direction and another force will be going in a negative direction. Therefore, mg, now I'm saying this to everybody because it's a good question. Someone was just asking, like, what about the negative in terms of gravity, right? What I want to tell everybody is the weight of an object is mg, and frequently mg you'll assign a negative direction. You'll frequently say that mg is pointing down, and you'll always say that mg is pointing down, and you'll frequently say that down is negative. So frequently the force on an object will be negative mg. Yes. So I'm saying yes to the person that's asking that in the chat, but I want to make this very clear as long as they're asking. Therefore, since you're going to put negative signs on entire forces shortly, we don't want to double count. We don't want to accidentally have two negatives making a positives. Therefore, I'm saying this to everybody. It's kind of important for the final exam and stuff. Therefore, G, that number G, 9.8, 10 meters per second squared, from now on, I consider that number just a raw magnitude with no negative sign at all. I never put a negative anymore into G. I just call G a number, and I multiply it by m to get a force called weight. And then often that, by the time I'm doing calculations, will have a negative on it. But that's an important thing. Like, it's a real question that someone's asking. So I'm saying G is not negative anymore to me. G is just a number. Often mg will be negative, but you see that once you set up a diagram. Okay, hopefully. And then and then Muhammad asked, would you say this is a physics definition or can it be applied generally? I forget what that was referring to, but if it was referring to weight, I would say weight is a force. Oh, yeah, yeah. Okay, yeah, generally, even in chemistry or bio, yes. Yeah. I mean, it comes from physics, but it's true. Okay, so now I know these are good questions. So now I know we have 5 minutes. So since I only have 5 minutes, let me give you the larger program and why these diagrams are so important. Like from now on, it's all about F net equals MA, or sum of the F's equals MA. Like that's where all of our calculations happen. But you see, I mean, you multiply M times A, you get F. The math is not the hard part. What you're going to find that requires thought is the left side of F equals ma means add up all of the forces acting on an object. So the issue, and that will equal the mass times the acceleration of the object. So the issue becomes, what are the forces acting on an object? And I mean, that's the issue for students and for physicists. Like that's the real question given a situation. What should I count as a force and what shouldn't I? And once I know for sure what all the forces are, and what their magnitudes and directions are, then I'll just add them all up and divide by m and I'll get the A. Like that's the deal. So the issue is identifying and enumerating the forces. So what we have is a very strict program for doing that, the strict program of diagrams. Okay. The two distinct types of force diagrams. The diagrams are all about identifying the forces so as to know what to plug in to the left side of F net equals MA. So I'm going to, since I only have 4 minutes, I'm not going to be able to like really break down these diagrams, but I'll give you the big overview so that you can at least start doing your homework and so forth. The two types of diagrams are system schema versus free body diagram. Now, honestly, If you start looking up on the web or looking for help or something on the web, free body diagrams are a lot more common, easier to find, like more standard. System schema is a slightly more modern technique, but it's there, it's on the web, whatever, and I can give you places to look up. But sorry, I'm really um, but the overview, system schemas are all about what objects are causing forces, and free body diagrams are about what directions are those forces acting in. And you always do them in this order. So they again, I'm watching the clock. I'm just trying to give you a big picture here. You will sort of have to look. I mean, and I'm going to do the details on Wednesday. You're going to kind of have to, for the moment, look things up on the web, I guess, to do this. But this, I'll tell you, it's not once you see it, it's not complicated. It's what a lot of you have been wishing the first part of physics was. That is, this is a set of procedures that once you know the procedures, you just follow it and trust it, and it won't steer you wrong. You don't actually have to think out of the box. It is a box for you. Okay, so with system schema, the idea behind a system schema is you you in a system schema, once you just draw a circle for the actual mass in question, the m in F net equals ma, the object of your attention. You draw like a little dotted circle for that, and then every single other object that's at all touching your object plus planet Earth, you draw a separate circle for. Like you start with a solid circle for Earth because it's always there. And then you draw a solid circle for any and every object that is touching yours. And by doing that, you'll see like if there's nothing touching your object, like our football a minute ago, then the only circle in your system schema will be a circle for planet Earth. But if a foot were touching a football, then there'd be a circle for that foot. So you literally just draw a circle for everything that's touching your object plus planet Earth. And that's a way of knowing, oh, this is how many forces are acting on my object. Then in the free body diagram, instead of those circles, you draw arrows. So you now get more specific and you look at in what direction are these pushes and pulls happening. And the whole idea behind all this is by the time you're done with the free body diagram, for every one arrow in the free body diagram, it becomes an F to plug into the left side of F net equals MA. And that's the idea. I know I'm sort of, that's a very broad view, but it is the end of class. So, look things up, do your best on the homework, and do a rough draft for Wednesday, and then you can expand it later. So have a nice night.
Thank you, you too.
Thank you.
All right, have a great day, Professor.
You too. Thank you all very much. Thank you for